All right, again, so what were the reasons I didn't like this drawing here? Yeah, the wedge and the dash, that's flipped. Should be the other way. And the other is the lone pairs. Now, there are three ways I draw the lone pairs. What were the three ways that I draw the lone pairs? Well, the lone pairs themselves, there are three ways I draw those. I draw, yeah, as a line, open circle, or dashed, or yeah, solid. That's going to go just around the central atom. So these are in the plane. Those, however, the chlorines, I'm not going to worry about drawing them, you know, inside or outside the plane, or whatever. You know, it's for the nitrogen being the atom here, but these terminal atoms we aren't going to worry about. So this is in plane. And then if I draw it like this is coming out of the plane. Out towards you. And if I draw them like this, these are going into the plane. So these are the three ways I draw. And so that would be applicable here. This lone pair is in the plane. This bond is in the plane. This wedge is sticking out. This dash is sticking in. Now, the lone pairs on the chlorine would just ignore, otherwise it's too much. That. Multiple bonds are the same type of deal, like you could see here. We'll just analyze this structure here. This one has two central atoms. This carbon is a central atom, so we'll just look at that carbon alone. When you look at that carbon alone, how many groups of electrons around this carbon? 3. You got a single bond, and a double bond, so that's 3 groups. Now, if we have 3 groups, what is its EPG? Okay, and then you look, then we have these 3 bonded atoms, so, you know, when we draw the Mg, what is the Mg for this? And so this is basically what I do when I'm analyzing these. The EPG is just going to be given by the groups. And so here, like, we have a double bond, single bond, 3 groups. The Mg is going to be dictated by the atoms. So when I look at the atoms, what do I have? The same shape. And so that means the Mg is also going to be trigonal planar. And so here, EPG is trigonal planar. Trigonal planar sets the angle. What's the angle going to be? 120. And the Mg will be trigonal planar. Now, there are 2 bond angles here. We have the HCH. The HCH angle. The HCH angle should be 120. And then we have the HCC angle. The HCC angle should also be what? 120. Except, you know, we have to look at potential distortions now. What's going to happen is, which of these balloons will be the biggest? Are they all going to be the same size? No. The double bond balloon is going to be bigger. If the double bond balloon's bigger, then that's going to push these two smaller balloons into one another, and it's going to make this angle smaller. It's going to make this angle bigger. This is a bit tricky here. I told you an extra pair of electrons is going to distort it, or a lone pair is going to distort it by 2 degrees. And so what happens here is the HCC angle goes to about 122 distorted. And so what's going to happen is that extra pair here is going to push the H away, increasing this angle to about 122. Well, let's look at this one here. This one also is going to increase by 122. And in a plane, all the angles have to add up to 360. So if this one goes to 122, this one goes to 122, this 244, that means that this one is going to drop to about 116. This is being pushed in 2 degrees by this, being pushed in 2 degrees by this, so it's going to shrink it by about 4 degrees. And so this is about 116 distorted. These are just guesstimates anyway, that we're doing based on Lewis structures. Now the other carbon's just the same. You know, the other carbon's going to be trigonal planar, and then, oh, this is not 8, this is F, sorry. Well, now that brings up another point. An H versus an F. F and H are different, right? But we treat single bonds like single bonds, no matter what the atom's bonded to it. And so if I change this to F, it's the same because, well, it's slightly different because an H and F have different electronegativities. And H is 2.0 and F is 4.0, but otherwise it's kind of the same thing. We're still going to expect distortions here. So if I make these F's instead, it's still single bond, double bond. And so the distortions are going to be the same. So we treat them as units like that. Okay, this other carbon is going to be just the same. The angles here. Well, what would I put the FCC angle at? The FCC angle should be 120, but it might be distorted to 122. And then the FCF angle should be 120. So actually not 120, because there are 2 of these. If this one's distorted by 2 and this one's distorted by 2, then this one's going to be distorted by 4. So it's going to be 116. So this angle is going to be about 116. This angle is going to be about 122, 122, 122, 122, and 116. Those would be the angles. Well, you know, these are, yes, we should compare that with experimental or factual data. So this is C2F4. Let's look at the bond angles from okay, that's different. Sorry, this is a different molecule. C2F4. I should have looked at the bond angle earlier. Well, it's called tetrafluoroethene. Tetrafluoroethene. Ultimately, we have to make sure that whatever our predictions are should match what the experimental data show. If the experimental data and the predictions are way off, then we have to rethink the basis of our predictions. And so this is something we check. And so this is a guess. We would take a look at the data. But that would require a search, a scientific search. What we're going to do is we're just going to move on. The next thing we're going to talk about are polarity of molecules versus polarity of bonds. You know, this is a very polar bond. Fluorine's a 4.0, carbon's a 2.6. So this is what we call a a polar covalent bond. So this is pretty polar. This one's pretty polar. This one, a carbon-carbon bond, is non-polar. These are polar here. And so let's take a look at polarity of molecules and polarity of bonds next. What does it mean? What it means is that, you know, carbon has a weaker pole than fluorine. And so if I look at the electron cloud here in this bond, lone pair is not going to do anything. Electron cloud is pulled towards fluorine. Fluorine's at 4.0, carbon's at 2.6. So fluorine is going to pull the cloud of electron density towards it. Like that. This is what we call a polar bond. The way we represent polar bonds is in two ways that we do this. One, there's going to be more electron cloud buildup near fluorine, which is going to give it a negative, and so we call it a delta. This is a little delta, delta minus. Whereas carbon's going to lack electron density, so that gets a delta plus. So this gets a delta minus, this gets a delta plus here. We can also show it by arrows. You know, if we show it by arrows, these are vector arrows, we have an arrow pointing towards the negative end and a positive tail pointing towards the positive end. So we get something like this. Okay, so we could do the same thing over here. Another fluorine. Another fluorine here. And so there's some polar bonds on this, you know. Okay. These are polar bonds because of the difference in electronegativity. Again, represent this in different ways. Delta plus, delta minus, delta plus, delta minus. Then we could use these vector arrows like this. Showing the direction of polarization. Now, to have a polar molecule, means that when you sum up the vectors, we're going to sum up these vectors over 3D space. And they don't equal 0, then it's polar. Non-polar molecule means we sum up over 3Ds these vectors, and they equal 0. And so one way of thinking about it is by a tug-of-war. But you're looking at a tug-of-war not just between two opponents. You know, you're looking at the tug-of-war in the whole molecule itself. If I just look at this bond here, then who's winning the tug-of-war? Fluorine. But what I do is I do a tug-of-war in 3 dimensions and add it all up. And so what's happening here is not just one tug of war. What's happening is 4 tug of wars. And so when we're doing this vector stuff, this is what we look at. I look at this fluorine here. This fluorine's pulling the electron cloud towards it, and so it's pulling up this way. And so if you have one person pulling this way, the whole molecule is going to be pulled up. But it's not just one molecule pulling, one atom pulling. We have a second fluorine pulling. And so if we just have these 2 fluorines pulling, which way is it going to go? Which way will the molecule move? If only these 2 fluorines are pulling, is it going to go up? Is it going to go down? Which way is it going to go? So if this one's pulling this way, this one's pulling this way, which way does the molecule move?
Straight.
It's going to move straight to the left. And so if these 2 are pulling, it's going to pull this direction, the whole molecule. This is called molecule polarity. However, these 2 are pulling it to the left. These 2 are going to be pulling it to the right. And it's equal and opposite because they're all fluorines. And so what happens is these 4 in this 4-way tug of war cancel each other out, and there's no net movement. And so even though this has very polar bonds, we call this a nonpolar molecule. Nonpolar molecule because all these add up to 0 in 3 dimensions. There's no net movement in this tug of war. So let's look at some other molecules, CH4. CH4, we saw this structure before, so we want to get some practice drawing tetrahedral geometry like this. Bond dipoles are very small. They're negligible. Why are the bond dipoles negligible? Because delta En is 0.4. Negligible means that, which one's more electronegative, carbon or hydrogen? Carbon. And so if I draw the bond dipole in here, the bond dipole is tiny. And since the bond dipole is so tiny, then it's negligible. It's pretty much a non-polar bond. Non-polar bonds are going to lead to a non-polar molecule. There's no tug of war, really. And so when I look at the electron cloud, it's pretty even. Just slightly polarized, but pretty even. And so all hydrocarbons are non-polar, no matter what the shape. Non-polar. All hydrocarbons are non-polar, no matter what the shape. So you could have the weirdest looking shape that's going to be non-polar, because here. You might think something like isopentane is going to be polar because things don't cancel out, you know. But isopentane in any hydrocarbon is going to be, all these hydrocarbons are non-polar. I don't have to do this vector stuff because the carbon-hydrogen bond is pretty much a non-polar bond. So non-polar bonds are going to lead to non-polar molecules. There's no real big tug of war going on. CCl4 is different though. CCl4, let's draw that. We'll draw carbon in the center, and then 4 single bonds attached to chlorine. Now the lone pairs on the chlorines I'm going to ignore, you know, the sticking out, sticking in the plane. I'm going to just draw them all the same. So this is CCl4. Now chlorine and carbon, those are polar bonds. Which one's more electronegative, chlorine or carbon? Chlorine is more electronegative. And so that means that I can draw like an arrow pointing towards the chlorines like this. So I got these 4 arrows like that. Now try to visualize this as a tug of war. Which way is it going to move? Is it going to move up, down, to the left, to the right, down? Looks like it's going to move down. But one way of imagining this is like this. Let's say you're stuck inside a ball. If you're stuck inside a ball, how would you want to arrange yourself? Would you want to arrange yourself linearly, like put your feet down here and your arms straight up there in a ball? Like, you know, have you seen those rolling balls that people go inside? Yeah, if you were stuck in one of those, would you arrange yourself linearly like this? Or would you maybe do trigonal planar like this? Or would you do tetrahedral? Tetrahedral, will you put 1 foot forward, 1 foot back, and then your arms out like this? What do you think would be the most stable arrangement? Tetrahedral. In fact, tetrahedral, you're pushing on all surfaces evenly because all the angles are exactly the same. So tetrahedral is what we call spherical symmetry. And so it turns out that if you're pushing at a tetrahedral angle like this, it's like being like this, you know? You're not going to go anywhere. You're going to be balanced. You're going to be stable. Versus if you're like this, you might start rolling, whatever. You know? And so this is, even though we have polar bonds, when we sum up these in 3 dimensions, this turns out to be a nonpolar molecule. Nonpolar molecule because they cancel each other out. Those polar bonds cancel each other out. And so CCl4 and CH4 are nonpolar. However, CHCl3 is polar. So let's take a look at CHCl3 next. So if we do it like this, carbon hydrogen we ignore. I mean, the arrow's too small. And so what we're going to have is we're going to have things like this. Okay, so do these cancel each other out? They don't. If we got 3 that are pulling down, which way is the molecule going to go? It's going to go down. And so when we sum up these, then we have what we call a molecule dipole. This is molecule or molecular dipole. These are called dipoles, by the way. These green arrows are called dipoles. And so we have bond dipoles, the green arrows. But when we add up the green arrows, we get this red arrow, which is the molecular dipole, which is pulling straight down. And so this is going to be what we call a polar molecule. We could do the next one like this. I'm going to draw this one with 2 chlorines. I'm going to make the chlorines, one coming up here, one to the side here, so we can see the dipoles a little easier. And then I'll have a hydrogen sticking out and a hydrogen sticking in like this. Again, carbon-hydrogen we don't draw a bond dipole for, but these ones we will. So which way is the molecular dipole going to point? If you add up those 2 reds, then which direction will the molecule move? Yeah, it's going to move up to the right like this. So the molecular dipole will be like that. So this is going to be polar molecule as well. CH3Cl. And do next, I'll put the Cl on the top like this, and then one hydrogen in the plane, one hydrogen wedged out, and one hydrogen dashed in. Again, carbon-hydrogen, we don't draw bond dipoles, but carbon-chlorine we would. Which way is this going to be? Well, these are 0, and we're adding that, and so the molecular dipole is going to be exactly the same.
Only for polar we do like the net dipole, right?
Only for what?
Only for polar?
Yeah.
The net, right?
If it's non-polar, we aren't going to do it. They call it the net dipole. They have a, so you can see that in the slide here. I drew it differently. No. Some of them. Carbon dioxide. Carbon dioxide has a polar bond, but it's a non-polar molecule because we have one arrow pointed to the left, one arrow pointed to the right, and so when you add them up, they add up to 0. And so CO2, even though it has very polar bonds, is non-polar because the bond dipoles cancel each other out. Whereas when we look at H2O, do the bond dipoles cancel each other out in H2O? So we have one bond dipole pointed towards the oxygen here, another bond dipole pointed towards the oxygen here. Do they cancel each other out? No. The net, it's going to be pushing up. Yeah. And so this is the net molecular dipole here. We should expect this to go up. This oxygen is pulling this way, this oxygen is pulling this way, so the net movement should be up. Let's get some practice drawing more complex molecules. Let's try to draw butane. We're going to try to draw butane. If I look at butane, I'm trying to draw it on a page. Okay, we have these carbons here. We're going to look at it one at a time. So let's look at carbon 1. How many groups around carbon 1? 4. Single bond, single bond, single bond, single bond. 4 single bond groups. That's going to give an EPG tetrahedral. And then we look at the atoms. Are the atoms in the same arrangement? Yeah, 4 bonded atoms in a tetrahedral arrangement. Do you see that? Except I'm going to draw it like this. When we start off the chain, I'm going to draw, I want to extend the chain this way. So the carbon-carbon is going to go like this. So how should I draw the hydrogens? One going straight up, and then one wedged out like this, and then one dashed in like this. We're looking at it from above. Okay, then the next carbon, this is what I'm going to do. I'm going to do, it's tetrahedral also. Do you see that? This one is tetrahedral also, with the bonded atoms. Do you see that? And so this is what I'm going to do. I'm going to do 2 in the plane, like this. And so I'm going to have this carbon-carbon bond in the plane, this carbon-carbon bond in the plane. That means one of these is going to stick out, and one is going to stick in. In tetrahedral, this is the way we do it, you know. 2 in the plane, 1 sticks out, 1 sticks in. So if you're stuck in the ball, you're like this, you know. You have 2 in the plane, and then 1 foot forward, 1 foot back. So these are your arms here. This is 1 foot forward, 1 foot back. You see that? Stuck in the ball. So we're going to put the hydrogens here. And the same thing here. We want to continue this in the zigzag pattern with the carbons. And so if we put 2 in the plane, that means 1 sticks out and 1 wedges back. Like that. And then here, we're going to have 2 in the plane. Actually, we'll do it like this. And then one sticks out, one wedges in. This. Do it like that. That's where it's going to terminate. They have it rotated. I could rotate this. So that's drawing a carbon chain. Hydrocarbon. Oops. Isobutane's the same. In the plane. This is in the plane, so one wedges out, one dashed in. This one that's wedged out, they don't put a hydrogen, they put a methyl group there. Methyl is also tetrahedral, so it shows this kind of shape to it. Let's draw ethanol next. Let's try to draw ethanol. You want to try? This methanol on the left, what's that on the right? Butanol, 4 carbons. Ethanol is going to look like this. It's going to be CH3 like this, and then CH2, and then an OH. So this would be the Lewis structure. Now try to draw a wedge dash structure for this, because the Lewis structure doesn't show the angles. So for example, if I asked you what is the COH angle, what would you say COH angle is? What is the COH angle? It's 109.5 undistorted. What's the HCH angle? The HCH angle. 109.5. You know, what's the CCO angle? CCO angle is 109.5. That's because I already saw what the structure is. Why don't you draw it though? It's a wedge dash diagram. Give that a go. Let's see.